Alright, so we are going to be working on thin lens tracing today. And even though this says lenses, which I kind of alluded to in lab, that lenses are clear, we're actually going to be talking about mirrors as well, because they abide by the same rule that lenses do. And so our goal is to find not only the size, but the orientation of an image that's formed either by a lens or by a mirror, because lenses and mirrors can do these funny things, right? They can make things seem bigger than they are, or they can even, like funhouse mirrors, make things different shapes, or even turn them upside down in special circumstances. And so what we're going to talk about today is, well, when do I get something that's big, or when do I get an image that's upside down? And we're going to give you a few fundamental rules to be able to do that. So first things first, a lens is something that transmits light or allows light to pass through. And so in these two images, you've got light coming in, and in this case, light kind of converges at a point. And then you've got a lens where light is coming in, and it refracts and goes through. And you notice with these lenses that light is refracted, particularly because of the shape of them that is enhanced. And so what was initially parallel light rays kind of bend as they go through this lens. What we see with mirrors is that light cannot go through, right? It never gets to the other side, but instead it's reflected back out. Last lecture we talked about plane mirrors and the law of reflection, and that was a really easy one, right? That the incoming angle is the same as the outgoing angle. For these, that's still true, but the difference is the surface of these mirrors that we're going to talk about today is curved, and so those kind of do some funny things to light. And you've probably experienced this if you've ever looked at yourself in a curved surface like a car door or maybe a spoon. The reflection is not like with a plane mirror. It's not a true reflection of what is actually there, right? The light gets distorted, and so you get a distorted image as well. And so we're going to be talking about all these cases today. Lenses and mirrors, depending on their shape, have special names. And so this will be important for you when you're doing word problems and I start talking about, say, like a converging lens. Well, you need to know what a converging lens looks like, and you need to know what a diverging lens looks like. The easy way for me to remember these is what they do to light. And so a converging lens makes light converge or come together. And a diverging lens makes light go apart or spread away from each other. If that doesn't work for you and you can't just memorize that, the other thing that you can look at is kind of the shape of the lens from the middle to the end. And so these edges seem to converge towards the ends, right? And then these edges seem to diverge or go away from each other at the ends. And so either of those ways to memorize what these lenses, which lens goes with which name, either of those ways work. Right, so we just talked about converging lenses and diverging lenses. Mirrors kind of come in the same shapes, but we actually have different names for them. And so if this shape is a mirror, we say it is a convex mirror, or it's curved outwards, right? And so as light comes in, it wouldn't go through like with a converging lens, it would just bounce off. The mirror name for this shape is a concave mirror, and this is easy to remember because like caves go inward, right? And so there's this little opening kind of inward shape to that mirror. All right, so your job is to know what shapes go with what names for mirrors and lenses. All right, and then a little bit more vocabulary. This is going to help you with your formulas. And so what we see is that in their formulas, we have some variables that start to look really similar, except some of them have apostrophes. And so I'm going to take a second and just kind of explain that in terms of this converging lens picture. So all lenses and mirrors have what we call a focal point. And a focal point depends on the individual mirror or lens. The focal point is going to be really, really helpful for us in talking about where an image gets focused. And so we'll start talking about these little light rays, and you'll notice that 2 of these rays are going through focal points, and that'll be important. How far the focal point is from the lens depends on the lens or mirror. But we still label all of them with this F, right? Not to be confused with frequency of waves. We also have what we're going to call the optical axis. And the optical axis is just this thing, this line right here that goes through the middle of the lens. And it helps us draw accurate pictures to figure out where the image in the mirror is going to end up. And so the optical axis is just this flat line. All right. We then have these 1, 2, 3 groups of variables, the S, P, and H. All of these without an apostrophe. So all of these, I should have put those together. That's okay. All of these go with the real object, to the actual thing in front of the mirror, right? And then all of these things, which pretty much look the same, except they've got this little apostrophe, go with this side. And so for a converging lens, it'll be on this side. It's not always on that side, but this is where what we see occurs. It's not the actual physical object, it's just the image of the object, right? And so S represents the distance from the object to the mirror, and that's always going to be measured in meters. And then S prime, or S apostrophe, is the distance that image seems to be behind the mirror. So we talked about, like with plane mirrors, you know, if I am 2 meters in front of the mirror, then my image seems to be 2 meters behind the mirror. Let's clean that up. There we go. So my image seems to be 2 meters behind the mirror. Once we start curving the surface of mirrors, this is not always true. And so that's why we're going to go ahead and start making 2 variables for this. P is the point on an object. And so it's the point of the object where we draw rays coming from. We usually, just as a convention, use arrows in our diagrams, and the top of the arrow is the P. And then P prime, or P apostrophe, is where we see the image of the same point, right? And so in this particular picture, P, our object, is upright right here, but once it passes through this lens, it makes a little upside down image. And so it is what we call inverted. P prime is inverted from P. And then specifically when we talk about lenses, the height, H and H prime, of an object can change in a mirror, or a lens. So H is the true height of an object that's looking into a mirror or lens, and then H prime is how big that thing appears to be. Right. We also have a little bit of vocabulary. And I'll continue to use this as we go through the lecture. These 2 go together. The image formed, so this little upside down arrow in this case, the image formed by a lens or a mirror can be described as either a real image, or it can be described as a virtual image. And so a real image is where the rays actually converge. And so in this picture, the rays actually go through the lens, and the lens focuses them so that these rays actually come back together at the end, and so we get a real image. A virtual image we'll explore when we talk about diverging lenses. A virtual image forms when rays seem like they're coming from somewhere. And so when rays seem like they're coming from somewhere, we're going to use dashed lines instead of solid lines. So you'll know that these are not actual rays, it's just kind of their path, right? It's not where the light is actually going. And then images can furthermore be described as being upright in the same orientation as the original object, or they can be called inverted. And so like this is a good example of an inverted image. I've got the actual thing is pointing upwards, but the image that is formed from this lens is upside down. And so we would call that an inverted image. And so for this one, we would say that this is a real and inverted image, right? And so we use one of these terms to describe it and one of these terms to describe it as well. All right, so moving forward from here, we'll be talking about all of these variables. It might be really helpful to you to pause the video, make a little list, and do your vocabulary words at this point to help yourself out. All right. So for all of these cases, for converging and diverging lenses, as well as concave and convex mirrors, they've all got a focal point, they've all got an optical axis, and they're all going to have this real object with point P. For each scenario with these 4 different kinds of optical instruments, there are always going to be 3 special rays, and these behave pretty similarly. But I'm going to go through every possible example with you and pay very close attention. And so this first example of the 3 special rays, these rays are very special because while there's light technically emanating from everywhere at point P in all directions, there are 3 very specific rays that we can use to find out where the image of P, so we will call this P prime, is going to be located and how it's going to be oriented. Right, and so this first example of the 3 special rays is going to be for a converging lens, C-O-N-V, lens, with object beyond the focal point. Alright, so by object beyond the focal point, all I mean is that these focal points for this particular lens are located here with the F's, and this object is farther away. It is, if I'm starting at the lens on the optical axis, it is past the focal point. Alright, and so you kind of explored this in lab. The easiest one and the easiest of the 3 special rays is this ray number 2. Any ray coming from point P, wherever that may be, and traveling through the center of the lens is not refracted. It just continues on in a straight line. And you saw this the other day in lab, that if you shine a laser right through the middle, that's the only point that it goes completely straight through at. Right? And so that's always the easiest one to draw. My second favorite is the special ray number 1. And so special ray number 1 says that any ray coming in perpendicular to the surface of the lens, and so forming a right angle, right? We also sometimes call these parallel rays because that's typically how they come in. So a parallel ray coming in gets refracted through the far focal point, right? And I can actually kind of, when I draw, I keep going. And then the point where these things cross is the important part. And then special ray number 3 says that any ray coming through the near focal point gets refracted parallel to the optical axis. And so what we find as we draw these 3 very special rays is that there's this really interesting part where they all come together, right? And where they all come together is where the corresponding point P and P prime will occur. And so what I know is from these converging down here, what I'm going to get from this situation is a real and inverted or upside down image. So it's real and it's inverted. Real, again, meaning that these rays actually do cross here, right? It's not a fiction of our imagination. They actually cross there. And so this whole viewing screen thing, if I have, like, if this is a projector, I want my screen to be right at this point where those rays come together, because then my image is going to be in focus. And if I put my screen here or here, I'll still kind of see the image, right? Like, I've got all these rays coming in, but it's not going to be focused. It's going to appear very blurry. And in chapter 19, this is where we start talking about eyes. If you have blurry or bad vision, well, this is why. Your converging lens in your eye is kind of the wrong shape for your eyeball, and so the back of your eyeball doesn't fall right where those rays converge, and so what you see ends up being blurry. Alright, but that's next chapter. I'm going to go on to the 3 special rays for another type of lens. Alright? So, we're going to talk about now the 3 special rays for, this is still a converging lens. Oh, and there's the word lens already there. So a converging lens. But this time, our object is going to be closer to the lens than the focal point. And so we've got a focal point here and here. This will be our near focal point. This will be our far focal point. And as you can see, our actual object, the real object itself, is between the focal point and the lens. Alright, so we've still got kind of my favorite one, always the easiest one, is this ray that goes right through the middle of the lens, just keeps on going. Alright, and the other really kind of easy one is this parallel ray coming in, gets refracted through the far focal point. Alright, good deal. But now we're to the hard part. So usually what we'll say is that, well, let me go back and kind of show you where I was at. So I'm on this one. We've done 1 and we've done 2. Usually what I just told you is that if something goes through the near focal point, then it gets refracted out parallel. But in this situation, oops, there we go. In this situation, I can't really make something go through the near focal point. It just doesn't work. And so what I do is I lay down a ruler and I say, okay, well, that focal point is behind me. But what I'm going to do is lay down a ruler towards the near focal point, and I'm going to say, okay, this ray technically lines up with the near focal point. Alright, and then once I get to my object, I'll just continue on and draw the rest of that ray until it gets to the lens. So it's kind of the same rule, I just have to work backwards a little bit. So something that is in line with the near focal point, a ray that's in line with the near focal point, gets refracted out parallel. But then, oh my gosh, oh no, I don't have a place over here where any of these rays come together. Oh my god, where is my image? And so it seems like maybe this lens doesn't work. But as long as you follow these 3 special rays for converging lenses with objects inside the focal point, it actually kind of does work. And so it just doesn't work on this side. It works on this side. So what we'll do is we're going to take these 3 rays, and after we've refracted them, and we're going to trace them backwards. So okay, so they definitely don't meet up over here. But what if I take my ruler and I kind of lay it down and trace them backwards? Now, the rays themselves don't actually go backwards, right? I'm just kind of extrapolating and trying to figure out what's going on here. So I'm just drawing these dashed lines. These are not real light rays. We're just saying where they come from. Oh, okay. And then I do have a place where they come together over here, right? Bingo! So what was my point P actually forms behind the actual thing. And so this is really interesting because now we are on to talking about virtual images. So this image is virtual, and it is upright with regards to the real thing. So it is a virtual and upright image, right? This original one was pointing up, and, well, this one is pointing up. It's above the optical axis. Now, it might seem weird, like if I have these, like, rays, right, that don't actually converge. Well, I can't focus them on a screen, so what good is any of this? Well, these kinds of lenses are actually what make our magnifying glasses and telescopes and microscopes. And again, kind of along with eyes, we'll talk about this kind of situation a little bit more in Chapter 19 when we talk about telescopes, microscopes, all that good stuff. But for now, I just want you to know how to trace them, and that this is a virtual and upright image. Alright, moving on to diverging lenses. So this is a diverging lens with an object outside of the focal length. So again, our actual object is farther than the focal length for the mirror. Alright, so we've got our actual object here. And again, our three special rays. So I'm going to start with my favorite, which is the one that goes through the middle. Woo! Every single time. I've got it. Whew! Alright. The second one is that a ray coming in parallel, instead of being refracted through the far focal point, this time I've got to kind of trace back. It is refracted through the near focal point. And remember that dashed line is not a real ray, but it gets scattered in that direction. As soon as it crosses our lens, it's going to get diverged from the other rays. Alright, and then our last one is kind of the flippy-floppy. So something that would traditionally go through the far focal point, right? So I kind of line my ruler up with a far focal point and draw this incoming ray. Something that would traditionally go through the far focal point gets refracted parallel to the optical axis. But again, oh crap, I still don't have rays coming together over here. What is the problem? Well, there's no problem at all. A diverging lens is supposed to separate all of these rays. And so this is actually okay. We just have to do the same thing that we just did. We are going to take these and we are going to trace them back. Ooh, look, we already traced that one. Okay. And I'm going to take the end result of C and trace it back. Alright. And I'm going to take the end result of A and trace it back. And I do have a place where they come together. And so, or seem to come together. Again, these are not actual rays. And so we call this a virtual image. And not only is it virtual, it's pointing the same direction as the actual one. So it's going to be upright. Yay! Alright. Same thing. This is another diverging lens. So we've got a diverging lens because those edges are spreading apart, or because they separate the rays out here. And this time, though, we're going to be considering an object that is inside the focal length. So again, that actual object is between the focal point and the lens. Alright, so favorite ray, right, is the one that goes through the middle, because I know it every time. Woohoo! Alright. the next one, oh, I'm sorry. So, I'm sorry, this is my image. This is my object, but even still, this one that goes through the middle, woohoo! I know it every time. Alright, good deal. Then, the ray that is coming in parallel to the optical axis gets refracted through the near focal point. And so I just lay my ruler down and then, whoop, there it goes off into outer space. And lastly, the ray coming in through the far focal point. So kind of line your ruler up with a far focal point and draw that ray coming in. Far focal point, there we go. Gets refracted out parallel. Again, I don't have these lines converging on this side. That's okay, because as I trace them back, they definitely do converge at this point. And again, I'm getting this upright and virtual image. It's just smaller, and so this is still virtual. Virtual because those rays don't actually go there. They just kind of seem to come from that point as we trace them back. So this is virtual and upright. Alright, so we are going to start our discussion of mirrors with concave mirrors and images outside of the focal point, which is the normal situation. Something's got to be pretty close to be inside the focal point. So with a concave mirror image outside the focal point, we've got my favorite ray, and my favorite ray is going to go to the center of the mirror. Now, because it's a mirror, it's not going to continue on through. That's only for lenses, but I still like this ray a lot because, well, it leaves at the same angle that it came in at. Yay! Alright, my next favorite one is the one that goes, let's see, incoming parallel ray to the mirror. And this is going to get refracted through the near focal point. And so, there we go. It's going to get refracted through that focal point. And then, if I have something that's coming through the near focal point first, and then hits over here, it is going to be refracted back out parallel. Alright. Oh, geez, I did a really bad job drawing this. Let's see. Alright, so this is kind of funny. I did a not so great job of drawing this. When you draw it on paper, it's going to be a lot easier to use a protractor and figure out the actual angles. Let's see, mine got really messed up here with my favorite one. Incoming ray gets refracted out at the same angle, and so that should have looked a little bit more like that. And then, okay, now we've got winner, winner, chicken dinner. If this was point P, then this is P prime, which means that this image is actually upside down, and it is a real image because these rays actually converge here, and so this will be real and inverted or upside down. Alright, moving on to our other option for a concave mirror, which is where our object is inside of the focal point. And so again, with my favorite ray, hopefully I don't botch it too bad, incoming and outgoing gets reflected. Alright, and then I'm going to have a parallel ray coming in, parallel ray coming in, and then the incoming parallel ray is actually, and this is going to be hard, I've got to pretend that it's going to, that's so narrow, hit that near focal point. There we go. Alright, so it is going to go through that near focal point. There we go. Alright, I'm going to Extend that one on out so you can see it a little bit better. And then our last one is one coming through the near focal point is going to get refracted out parallel. And again, this is kind of an impossible situation. We've seen this before. So what I'm going to do is lay down a ruler this way, and it's going to go through point P, and then this is going to be my actual ray, and it'll get refracted out parallel. Okay, so bad news. We don't have anything coming together over here. Oh no, but it's okay. What do we always do when we don't have these things kind of coming together? Well, you've got to trace the reflected rays back, and so this is actually going to have an image form. Let's see. I'm going to trace this guy back. I'm just going to keep tracing because I don't really know where that image is going to end up with my excellent artistic skills. And that one is going to get traced up. Okay. I'm getting a pretty good idea, but I'm going to do this third one just in case. Alright. So I do have a winning spot. This one didn't get botched as bad. So if this is point P, then this will be point P prime, which means that I have a virtual image, first off, because because these rays aren't actually here. They can't go through this mirror at all. They just appear to be coming from here. So I've got a virtual and an upright image. Yay! Alright, last case is where we've got a convex mirror. And a convex mirror only has one situation, because this is the outside of the mirror. The focal point is technically somewhere inside the mirror, and so I don't really have an inside and outside of the focal point scenario. I've just got an outside of the mirror scenario. Alright, and so my favorite ray is the one that goes right to the middle. Let's try to do this good, Ellis. Alright, and it comes right back out at the same angle. I think that's not so good, but we'll see where it ends up. You know the idea. Alright, and then I've got a parallel ray coming in, and that parallel ray is going to get reflected out, and it's going to be in line with that focal point. So the actual ray is going to get reflected up that way. Alright, last special ray is the one that goes through the focal point. And so I'm going to kind of lay down my ruler from the focal point to point P here. And I'm going to find that ray that goes through the focal point. But it does it as an incoming ray. And so it's going to be like that. And then that gets reflected back as a parallel ray. Alright, and so, again, I don't really have a place where these things are coming together over here at all. So, sad face, but what do I always do if I don't have those coming together? Well, I first need to check my three rays, but then I'll take this one, and this one, those reflected rays, and trace them back into the mirror. And so I'm going to trace this guy back. Alright. And I'm going to trace this guy back. That one's parallel-ish. Alright, and then I'm going to take this last one, the purple one, and trace it back. Alright, and I do have this little place where things are converging, and so that's going to be my P prime. And it's little, but it's there. And it is going to be a virtual, again, because those rays can't actually get behind the mirror, they just appear to converge there. This is going to be a virtual upright image. Alright, and so my suggestion to you is to take all of these scenarios and put them on your formula sheet. And in fact, I've given you space to do that. You also have some homework practice problems. These are things we're going to do in class, but if you want to get a head start, go ahead and do that. Especially for these lens and ray tracing things, it's going to be really important that you use a ruler and maybe even some graph paper and a protractor. That's going to make your images turn out a lot better than that first one that I tried. So it's going to make sure your angles are right, it's going to make sure things are parallel, and you need to measure out the actual distances too. So be sure to, in these problems, draw the correct shape of the lens, whether it's converging or diverging or concave or convex mirror. Draw the right shape. Know whether you're dealing with a lens or a mirror. You'll draw the optical axis, and then you'll draw the focal points and label them so you don't forget what they are. And then you draw your actual object, go back and figure out your 3 special rays. And if you get confused about those 3 special rays, like I said, I really encourage you to put them on your formula sheet. But they're also at the bottom of page 602, that summary page at the end of the chapter, and you'll find them on the bottom left. So I look forward to seeing you in class for some lens and mirror ray tracing practice.